The purpose of this experiment is to study the electromotive force induced when a magnet falls through a coil. We used PASCO's 850 interface on which we connect a voltage sensor and PASCO's CAPSTONE software to process the measurements. We also used coils with different numbers of turns, at the end of which we connected the voltage sensor. In addition, we used bar magnets. Activity 1. The dependence of the electromotive force of induction on the polarity of the magnet. We drop a bar magnet vertically down through a coil with 300 turns. We observe the creation of an electromotive force by induction at the ends of the coil, as there is a relative movement between the magnet and the coil, resulting in a change in the magnetic flux. According to Faraday's law, any change in the magnetic flux creates an electromotive force by induction, which is proportional to the rate of change of the magnetic flux. The value of the electromotive force changes as the magnet performs accelerated motion, and the rate of change of the magnetic flux passing through the coil is not constant. The induced electromotive force takes both positive and negative values. As the magnet enters the coil, the magnetic flux increases, and when it exits, it decreases. The maximum value of the electromotive force during the entrance is less compared to that during the exit of the magnet from the coil. This is because the speed of the magnet entering the coil is less than the corresponding speed when the magnet exits the coil. Therefore, the rate of change of the magnetic flux at the entrance is smaller than the corresponding rate of change of the magnetic flux at the exit. The total area of the plot is 0, as the change in magnetic flux when the magnet enters the coil is exactly opposite the corresponding change when the magnet exits the coil. By letting the magnet fall vertically from the same height with opposite polarity to before, we observe the creation of electromotive force by induction with opposite polarity. Activity 2. The dependence of the induced electromotive force on the height we drop the magnet from. We drop the magnet through the same coil with the same pole facing downwards, but from two different heights. We observe the creation of an electromotive force with the same polarity but with larger values for the larger height. This is because the speed at which the magnet passes through the coil is greater, resulting in an increase in the rate of change of the magnetic flux. Activity 3. The dependence of induced electromotive force on the number of turns of the coil. We drop the magnet with the same pole facing downwards from the same height, but using a coil of 1,200 turns in place of 300 turns we used before. We observe that the induced electromotive force is quadrupled. Thus, the induced electromotive force is proportional to the number of coil turns. Activity 4. The dependence of the induced electromotive force on the intensity of the magnetic field of the bar magnet. We drop two magnets with the same poles facing downwards at the same time through the coil, thus increasing the intensity of the magnetic field. We observe that the value of the induced electromotive force increases. Then we drop two magnets with opposite poles facing downwards at the same time into the coil, thus reducing the intensity of the magnetic field. We observe that the value of the induced electromotive force decreases. In the case where the magnets have approximately equal magnetic field strengths, the electromotive force created is almost zero. Activity 5. The study of the electromotive force of induction when the length of the coil is much longer than the length of the magnet. We drop a magnet through a much longer coil. We notice that there is a period of time during which the magnetic flux does not change and the induced electromotive force is zero.